We'll examine the bulk copolymerization process of styrene, alpha-methylstyrene, and acrylic acid in an autoclave pressure reactor. The reaction takes place in a sealed autoclave pressure reactor, which can withstand high pressure and temperature conditions. We begin with our three monomers, styrene, alpha-methylstyrene, and acrylic acid. These monomers are fed into the pressurized vessel to begin the copolymerization process. We add 10 to 30% xylene solvent to control viscosity and improve heat transfer during the reaction. The reaction temperature is maintained between 120 and 150 degrees Celsius, which is critical for this copolymerization. As the reaction proceeds, pressure builds up in the sealed reactor. The polymerization occurs through a free radical mechanism. First, the initiator breaks down into free radicals due to the high temperature. These radicals then attack the monomer double bonds, initiating chain growth. The growing polymer chains incorporate all three monomers in a random sequence. As the chain grows, it creates a copolymer with varying sequences of the three monomers. The reaction conditions, including temperature between 120 and 150 degrees, pressure, and monomer ratios, determine the final copolymer properties. The glass transition temperature, or TG, is a critical property of our copolymer, ranging from 120 to 150 degrees Celsius. Below the glass transition temperature, polymer chains are rigid and the material behaves like a hard glass. Above the TG, chains gain mobility, making the polymer more flexible and rubbery. The glass transition occurs over a temperature range rather than at a single point. This transition region is key to many of the polymer's applications. The molecular weight distribution of our copolymer is carefully controlled to be between 9,000 and 12,000 grams per mole. This graph shows the relative abundance of different chain lengths in our polymer. The target molecular weight range affects critical properties of the polymer, including mechanical strength, viscosity, and processing behavior. Chain length directly impacts polymer properties. Shorter chains provide better processability, while longer chains contribute to strength. The acid value of our copolymer ranges from 210 to 230 milligrams of potassium hydroxide per gram. This property comes from the carboxylic acid groups in the acrylic acid units of the polymer backbone. The acid value is measured through titration with potassium hydroxide, where the carboxylic acid groups react with KOH to form salts. The acid value is crucial for determining polymer reactivity, adhesion properties, and solubility characteristics. Quality control testing ensures our copolymer meets all required specifications. Differential scanning calorimetry, or DSC, measures the glass transition temperature by detecting changes in heat flow. Gel permeation chromatography, or GPC, analyzes molecular weight distribution by separating polymer chains based on their size. Titration with potassium hydroxide determines the acid value by neutralizing the carboxylic acid groups in the polymer. Let's examine the key applications of our copolymer with its specific properties. In coatings, our copolymer's high glass transition temperature and acid functionality provide excellent durability and adhesion for industrial and automotive applications. As an adhesive component, the controlled molecular weight and carboxylic acid groups enable strong bonding properties for laminating adhesives and pressure-sensitive tapes. For specialty materials, the tailored reactivity and thermal stability make our copolymer ideal for textile finishes and paper modifiers.